Ed with the Kaizen effect, and today I'm going to start my lessons on fluid mechanics. And this is going to be an introductory lesson that is going to go over some preliminary ideas that you need to get before we go into more convoluted subjects in fluid mechanics. And what I want to begin with first is talking about different analytical approaches in fluid mechanics, and then I want to extend that over to deriving the Reynolds Transport Theorem. So let's get started on the analytical approaches you can take in fluid mechanics. So there are two main approaches you can take. Basically, you can take a differential analysis, or what is most commonly done in fluid mechanics, especially in engineering, you can take a control volume analysis. And depending upon the approach you choose to take, you're going to have different information you get from those analyses, and they're going to get you to different results more efficiently than other analyses. So in order to drive this point forward, I'm going to consider an example. So let's consider let's assume we have some kind of mixing chamber here, and we have some flow entering the chamber, and we have some flow exiting the chamber. And furthermore, let's assume that we're a chemical engineer, and we're interested in taking a look at how these fluids, so we're going to assume we have two different chemicals coming in, how those chemicals or species mix together, and how that allows us to get some kind of mixture coming out. So we're going to be analyzing the mixture process. And in that case, you could take two different approaches. So if you're a chemical engineer and you're interested in the processes or how properties vary given the fluid flow in the region that you're going to analyze, what you want to do is you want to perform what is known as a control volume analysis. And the way in which that works is basically you can consider your fluid properties in any given region. In this case, I have drawn this control volume, which is in yellow. So we're interested in how the fluid properties change in this mixing chamber. Because if you're very interested in the production of some chemical species, then you want to know basically how much of the mixture comes out, or the percentage of a certain chemical in that mixture. So you're interested in how these fluid properties are going to change within the region you're analyzing, right? So in that case, you'd want to consider the properties over your control volume, and that would most expediently get you to the result you're trying to look for. Now, there's also a different analytical approach you can take, which is known as a differential analysis. And this differs from a control volume analysis in the sense that we consider what's happening on a differential scale, so at very small scales. So we're going to track how the mixture or the mixing takes place on a particle basis. So when this fluid comes in, you're going to have some particles that are going to be flowing in, and the differential analysis tries to shrink down the region you're analyzing such that you can analyze the different particles that are, flowing throughout the region. Now, this becomes very important if you're a researcher and developer, if you're interested in more than just the production of the mixture you're trying to produce. For example, let's say you're trying to design this mixture chamber here, and you want to know maybe how the velocity profile varies. So maybe it's going to look something like this. Or maybe it could be a constant flow, right? And maybe based upon this flow, maybe you get eddies or vortices, which are basically when particles swirl around, and maybe that can help mixing. Or maybe you're interested in the pressure drop across this mixing chamber. So if you're interested in basically how the particles interact within the schematic you're choosing, then taking a differential analysis becomes more important. But it requires a lot more work in the sense that you have to solve partial differential equations, and the governing equation, which I will derive in subsequent videos, becomes the Navier-Stokes equation. Okay, so you have to solve that PDE. It takes a bit more work, but you get a lot more information out. So depending upon what kind of analytical approach you take, you're going to get a different number or a different set of information from that analysis, and you want to make sure you pick the appropriate analysis, either a control volume analysis or a differential analysis, such that the information you get from your analysis is tailored to what you're trying to determine and also allows you to get to that information as efficiently as possible. So now let's take a deeper look at the control volume analysis approach that I just talked about. And before we do this, we want to take a step back and recall how the conservation laws in solid mechanics are actually applied, because this is going to help us understand what's going on in the control volume analysis. So in solid mechanics, what happens is you usually take some system of particles and you analyze that in terms of conservation of mass, energy, or momentum. So when I say conservation of momentum, I mean like you take a force analysis, right? So the way this works is you usually have some kind of system. Let's assume that we have this system, which is a cylinder. Here we have a cylinder rod, right? And your system always coincides with the mass you're analyzing, right? Let's say the volume we're analyzing is this dotted line here. And since we're analyzing a solid particle or solid system, solid materials, this control volume, or rather the volume coincides with your system, with the mass, okay? And when you apply your conservation laws, you basically apply that to this system, and your volume coincides with the total mass in the system. So for example, conservation of mass. You say that dm dt equals 0. If you're not considering relativity, basically your mass is going to remain constant. You're not going to create or destroy any mass, right? So you apply that to this system, which happens to coincide with the volume, right? You can also do the same thing in terms of conservation of momentum. So suppose you have some kind of force acting here, we'll call it F naught. What you do is you consider Newton's second law, right? You take some of the forces in the x and y, and then you set that equal to your mass times your acceleration, right? So you would take this F naught, set it equal to ma, and then you have your equation of motion, right? Now, the good thing about solid mechanics is, again, I'm sort of beating this into the ground, but your volume that you're analyzing coincides with the mass at all times. If you're analyzing this eraser and it's moving, right, the volume of the mass and the system you're analyzing, they coincide, right? The boundaries don't move. They stay intact with the mass you're analyzing. Now, if we go into fluid mechanics, this setup sort of changes a bit. And this is what drives us to really take a look at the Reynolds Transport Theorem, which I'll explain in a bit. But if we look at fluid mechanics, and I'm going to look at the example I had previously right here with the mixing chamber, you know, if we want to analyze a set volume, the mass does not always coincide with the volume, right? The system and the volume are not coincident, right? Because let's suppose we have some fluid flowing in here, we have some fluid flowing out, and our system might, you know, it might be constituted by maybe this portion here. And the system is going to flow and it's going to keep propagating, and our boundaries are going to change. They're not fixed, right? So, for example, if we take maybe a drum, a cylindrical drum, we fill it up with some water, like so, and then we turn this and pour out all that water, then the system of particles we're analyzing, you know, the boundaries are going to move because the shape of this is not definite. It takes the shape of the container it's in. So as a result of that, you know, we might have a ton of water maybe on the ground, maybe something like this after we pour it out. And that's a different boundary enclosing the system, right? So as a result, we can't apply the conservation laws that we have from solid mechanics here because these boundaries and the volume do not coincide with the mass we're analyzing. So the main point in deriving the Reynolds Transport Theorem is to figure out how to relate the system properties to the control volume properties. So, it's sort of convoluted to take a look at how the boundaries change and keeping track of how the boundaries change. We want to do an analysis over a given region. For example, if we go back to what we were talking about in the mixing chamber, we want to analyze how the properties change in this volume, not how the system changes as a whole, like how it's flowing out here, how it's going to take those properties. We want to analyze what's going on in the control volume that we're interested in. So we need to figure out some way to apply this nice framework of the systems to a volume. So the main point of basically the Reynolds Transport Theorem is to take some property, maybe B, some system property, and figure out how it relates. So we want to form some kind of function of how the system property relates to the control volume property, because if we can do that, then we can take our properties in this control volume, shift it back to the system, and that will allow us to apply these nice properties or conservation laws for systems that we developed in solid mechanics. So that's the goal here in this lesson. We're going to try to formulate some kind of relation such that we can relate our control volume properties to our system properties, and that will allow us then in subsequent videos to apply conservation of mass, conservation of momentum, and conservation of energy. So in order to relate the properties over the control volume to the system that we're analyzing, what I'm going to do is I'm going to consider this one-dimensional example and use that to derive the one-dimensional Reynolds Transport Theorem. And then I'm going to take those results and extrapolate in another video over to a generalized result for the Reynolds Transport Theorem. Well, let's take a look at the example we're going to consider now. So in this example, we're going to assume we have one-dimensional flow, okay? So we're going to assume we have this velocity profile entering maybe two plates or a pipe where we have boundaries at the top and the bottom. So we're going to have this velocity profile that is not going to change in the y direction, but is going to flow in the x direction along this system we're analyzing, okay? And furthermore, we're going to separate the system. So we're going to assume right now we have a ton of fluid in here, and we're going to separate that system, that fluid, into three separate systems. And I'm going to call system 1, 2, and 3. And at time t, the initial time when we start analyzing the problem, we're going to say that system 2 corresponds with the volume we want to analyze. So the control volume here, which is depicted in yellow here. And again, just to reiterate, a control volume is a region that we specify that remains constant in volume that we want to analyze, okay? So initially, at time t, system 2 is going to coincide with our control volume. And as you would expect, if we had this velocity profile coming in and flowing through this region from left to right, you would expect these systems, so system 1, 2, and 3, to move to the right as time progresses, right? So as a result of that, system 1 is going to move into the control volume, system 2 is going to move out of the control volume, and system 3 is going to move further along, basically the system we're analyzing. So at a time t plus dt, where dt is a small amount of time, so in other words, after a small amount of time has passed, what you would expect to see is the following scenario. So system 2, you can see, has moved out of the control volume, and system 1 has moved into the control volume, okay? And furthermore, we see a portion of the control volume is composed of a portion of system 1, which is this yellow hashed line here, and a portion of system 2 has moved out of the control volume, okay? So what we can do is we can consider the properties in these systems, or the control volume at time t plus dt, with respect to what was going on initially at time t. Okay, and based upon those changes, we can figure out how the properties in this control volume relate to the properties in a given system, which we will use as system 2. But in order to do that, we are going to need to figure out how we can evaluate properties in a given system. And then after we know that, we can apply basically the procedure I just outlined here and get to the result we're trying to get to. So in order to compute or figure out all the properties within a given system or region, which is what we're going to have to do in order to basically derive the Reynolds Transport Theorem, we have to first take a look at intensive and extensive properties and what the difference is between the two. So let's do that now. So an extensive property, as the name implies, is a property that is dependent upon the size or extent of the region that we're analyzing. So if you have a large region that you're analyzing, you'd expect to have a large quantity of some kind of property, right, of the extensive property. Conversely, if you have a small region you're analyzing, you won't have a large quantity of the property you're analyzing. So as an example to really illustrate this idea, let's consider again, maybe we have some cylindrical drum, some bucket that has some fluid in here, and inside that fluid, we have different extensive properties, right? And those extensive properties are really tied to the size of the system, okay? So we're going to use capital letters to denote extensive properties, and we're going to say that initially we have some kind of extensive property, and then we're going to take this bucket and we're going to dump it into two other buckets, okay? So this is going to go into there, and it's also going to go into here. So imagine we have half of this entire big bucket, in this bucket, and this bucket, and you'd expect your extensive properties to have basically half of this. So examples of extensive properties are mass and energy, for example. If you take all of the properties in this system, you dump it into these two systems and reduce the extent or size of your system, you get a fraction of that extensive property, which makes sense because, we're going to have 1/2 of the mass in there and 1/2 of the mass in both of these. Similarly, we're going to have half of the energy that is contained in here in these two buckets. So you can see extensive properties are properties that are basically tied to the size of your system, the extent of it. So how does this differ from intensive properties? So let's take a look at that. So with intensive properties, these are properties that are intrinsic to the material you're analyzing. So examples are like, maybe the density or the temperature, in the sense that throughout this domain, you're going to have the same amount of that property, provided that it's uniform, like that we have uniform density. So if you take like an entire system, intensive properties are not contingent upon the size or extent of the system. If you took this system, did the same thing, dumped half in here and half in here, let's say this has original density rho and temperature T, this system would have density rho and temperature T, and this would have the same exact thing. Because if this is at 70 degrees F, this, just pouring out there is not going to change its temperature, right? It's going to remain fairly constant. Same with the density, provided that we have a uniform material that we're looking at. So intensive properties do not depend upon the size of the system. They depend upon basically, one definition throughout the entire region. So if we take this framework, this gives us a very nice way to basically figure out the total amount of a given property in a system that we're analyzing. So basically, if we call the extensive property big B and the intensive property little b, and we also analyze a subset of intensive properties which are called specific properties. And when I say specific properties, that means I'm talking about on a per mass basis. Then what we can do is we can relate the two as follows. So we can take our mass multiply by our intensive property, and that will give us basically the extensive property we're interested in, right? So to streamline this and make it a bit easier to understand, let's assume that we have some kind of region we're analyzing, right? And this region has an extensive property B. So the total amount of the property we want in the fluid is B, okay? And let's suppose this has a total amount of mass M. And it also has a intensive property B. So if we take the total mass of this, and the intensive property is some property divided by mass, and it is the same here as it is here, as it is here, so it's the same throughout the region, what you could do, you could take basically your total mass, multiply by your intensive property, and that's going to give you your extensive property. So let's label some things here, make it a bit more formal. So we have B as our intensive property, big B as our extensive property. And what you can do is you can analyze this at any kind of size you want, right? And that size is going to dictate your extensive property, because the extensive property depends upon the extent of the region you are analyzing. So, you know, we can shrink this down. Maybe we want to analyze this infinitesimal region right here. So, you know, this could have a mass dm, and you have an extensive property dB. So we can just take this, we can analyze that small region, take the same framework, we could do something like this, okay? And what's really good about this framework and intensive properties versus extensive properties is the idea that we can break this mass down into something that allows us to perform the calculation very easily, because dm, you know, it's not as easy from a geometric standpoint to measure the mass in our system, right? It's harder to figure out the total mass in this as opposed to, you know, figuring out the volume in this, because we could just take the length, width, and the height coming out, multiply that, and figure our volume. But with intensive properties, we can say there's a density throughout this that is uniform and constant, and that allows us to express basically this dm, or m, as rho times the volume of the system, okay? Because this is mass per volume times volume, that's going to give us our mass back, right? So, you know, you can also do this on a differential analysis. If we analyze a small box dm, it's going to have a size dv, and we can just say that dm is rho dv, right? So, what we can do is, any region we'll call this particle I, dmi, and dvi. We can just extend this to the following. Okay? And so we can shrink the analysis down to basically the small region we're analyzing. And we could do that here, 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 we could do that here. So, you know, this might be I equal 1, I equal 2. So the second one we analyze, this might be the third one we analyze, and the fourth one we analyze. So what you can do, if you keep doing that and add up all these, you can take a sum, right? So you could say, you could sum over every particle in this system, and you can say the total extensive property, B, the total amount in that region, is just the sum of I equal 1 to n, so the total amount of particles we're analyzing, the intensive property at the part we're analyzing, or the little domain we're analyzing, times the density inside that region, and then we can take that. Now, if I'm taking an infinitesimal approach here, the thing that I should be triggering from you, the response, is calculus, right? That's the framework of calculus, right? So if we take this sum, and we basically take the sum such that all these particles become so small, so we're going to shrink these boxes down to really small points in that region, what we could do is we could say that this is the limit as this gets as small as possible, and as it gets as small as possible, we're going to have to add up an infinite amount of these volumes. So what we can say is the limit as the total amount we're adding up goes to infinity of our sum from I equals 1 to n, bi, rho I, dv. Now, I guess to make this appropriate, I should have called this delta vi, and same here. When you do this, this is the definition of an integral, right? So we're adding up all these particles in here, and what we get is the v in this domain. We can call this our control volume, so we can, set the control volume of the region that we're analyzing, and we can just say that is the integral of vi rho I times dv, right? So that allows us to figure out any kind of property B in this system by basically performing a geometric analysis. So if we know the intensive property, we know the density, okay? We can drop these I subscripts here. We can figure out the total amount of property B throughout this entire region. And we can do that for basically what we're analyzing in the previous example I showed. We can apply this nice property to the problem we want, and that will allow us to derive the Reynolds Transport Theorem. So if we go back to the one-dimensional problem that we're really interested in, this gives us a lot of leverage. It gives us a lot of ability. And basically what it does is it allows us to determine the amount of property in each of these systems. And once we do that, we can figure out how those properties relate to this given control volume and basically perform some kind of conservation law over it. So before we do that, there's actually one more element we need to do that. And we can sort of take a look at that by looking at the example here. So as I explained previously, as the velocity flows through this system that we're analyzing, some terms, or basically a portion of the system, is going to leave the control volume. So a portion of system 2 is going to leave, which is represented by this yellow crosshash here. And a portion of system 1 is going to enter the control volume. So we need to figure out what portion leaves and what portion enters. That means we want to take a look at the flux terms that are being incorporated here. And in order to do that, what I'm going to do is I'm going to draw this box here. And basically, we know that if something is flowing through this system, what's going to happen is, as time progresses, we're going to get more of the system flowing out, right? We can see that here, because when delta t progressed, a portion of this system left the control volume. So this distance here is a function of the velocity, right? Because if we have a velocity v sub x that is constant in this direction, then we're going to have some kind of velocity here, v, right? And this length is going to be v dt, right? So the more time that progresses, the longer this flux term is going to get. So one way to really think about this is basically you have, like, if our area is constant, the flow is sort of pushing this out, and it's sort of like, it's like sweeping some volume basically through the region. So the amount that it sweeps by is v dt, which we have here. And we know that the area term is going to remain constant, right? So this area here is going to be the same on both of these faces, right? So in order to figure out the volume of this term that was swept, so basically this volume here, and I'm going to take the height coming out of the board, what you can do is you can just take volume as the constant area times, so basically the area is going to be this distance times the distance coming out. So it's basically the area of my hand, and we're basically sweeping that area to the length v delta t. So we can take the area we sweep times the length, and that gives us the volume of this region, or the volume of that region, and also that region, right? So if we want to figure out the extensive property B throughout this region, which we will need to perform some kind of conservation law, what we can do, we can use the nice framework we just talked about, extensive and intensive properties, right? So we can take basically B equals, or the extensive property B that we're interested in this domain, and we can set that equal to m times our intensive property B, right? We further reduce the mass down to B times rho delta V, right? And we have that volume term, right? And we could, I guess we could drop the differential, but you understand what I'm talking about. We're talking about the volume, this volume, the volume of the region we're interested in. So we could take this, plug it in, and we basically get B rho times our area times our velocity times delta t. So I'm going to denote this as B flux, and you can see if we take this term here, we will be able to figure out the total amount of this extensive property B in this region, and that will help us when performing the conservation laws that are needed to derive the Reynolds Transport Theorem. So now that we know how to compute the total amount of fluid property B in a given region, in addition to the fluid properties in the flux region, basically the region that is being fluxed in or out of our control volume, now we have all the ingredients that are needed to derive Reynolds Transport Theorem. So before we do that, what we're going to do is we're going to figure out the total amount of properties in the systems and the control volumes at time t and time t plus delta t. So if we back up a bit, the main purpose of what we're doing here is we're trying to relate the extensive property B of our system to the control volume we're trying to analyze here, right? And that's done because we want to apply those nice conservation laws that we have in solid mechanics and try to bring them over to fluid mechanics such that we can apply them to a given region that we're interested in, basically our control volume. So what we're going to do, we're going to figure out how the system property is related to the control volume property. And to do that, we're going to use these diagrams that we talked about previously. So just a quick recap. Initially, we see that system 2 coincides with the control volume. And then as the fluid flows in the x direction, what we find is that system 2 flows out of the control volume, which is represented by this hashed area, or I guess it's volume if we consider this coming out of the board. And a portion of system 2 comes into the control volume, which corresponds to this hash region here. So what we want to do is we want to figure out how the two relate at these two different times. So at system, or rather at time t, that's easy. We have that or rather, I guess we'll start with the control volume, the extensive property B of the control volume at time t. Well, we see that system 2 coincides with the control volume. So we can say that the two properties match up. But at this time, it's a bit different, right? We see that in the control volume, we have a portion of system 2, we have a portion of system 1, and we have to account for that somehow. So what we can do is we can take our control volume, our properties of the control volume at time t plus dt, we can take the properties of system 2 at that time, which is going to be this region. So let's write that up. So we have the properties of system 2, and I guess I forgot to write in system 2 here, at time t plus dt. And we're basically going to subtract away the term coming out, right? So we're going to have this flux term, so minus b flux out. So we want to take this system, we want to take away this hashed region, and we want to add on the portion from system 1 that is coming in. So this hashed region, right? So we want to add on to this, basically, b flux in, right? And if we look at this from a geometric standpoint, this makes sense. So we want to figure out the amount of intensive property B in this region, this control volume, at time t plus dt, and that can be found out by taking system 2, which is extending a bit out of the control volume, subtracting the bit that extends out of the control volume here, and adding the part of system 1 that comes in. So we see this term here is basically this region, and this term here is basically that region, and they all add up to the total amount of the extensive property B in the control volume at time t plus dt. So now what we're going to do is we're going to take those two quantities we just derived and use that to perform a balance over our control volume. So we want to figure out how the extensive property B changes in our control volume and use that to relate the properties in the control volume to the system such that we can apply those nice conservation laws from solid mechanics over a control volume. So basically, if we want to find the change in an extensive property B in a control volume, what we're going to be doing, we're going to be finding the derivative of the extensive property B in that control volume. So we can approximate this derivative as the following. We can take some time delta t, and we can take the definition we just had of BCD at time t plus delta t. That's our final state we're analyzing. And we can subtract away the initial portion of our extensive property B, and then we can divide by delta t. So this is an approximation, okay? So what we could do, we could take the nice terms we just derived, plug them in here, rearrange things, and then take a look at what we get. So again, this is sort of approximation, so I'm going to put an approximate sign right in there. So let's do what I just said. Let's take the properties we just derived, put them in, and see what happens. So at time t plus dt, we found that the control volume, or the properties of the control volume, are equal to the extensive properties in our system at t plus delta t minus the flux term that is going out plus the flux term that is coming into our control volume, right? And initially we found that the system, I'm going to put 2 in here because we're doing this over system 2. But as I was saying, initially we found that the control volume coincided with system 2. So we just get this guy here, okay? So what we can do, we can rearrange this. We can group the system terms and the flux terms. So what we end up with is, basically the system t plus delta t system properties at that time. And we also have the system properties at the initial time. We also have these flux terms. So I'm going to rearrange this a bit. Take the influx term first, subtract away the outflux term, divided by delta t. So we know what these terms are because we derived them previously, right? They're just B rho A V delta t. So our delta t's are going to cancel out, which is pretty nice. And then we can do some nice stuff with this. So let's focus first on this term here. So our system term, you can see that this looks very familiar. It should look familiar to you because it looks like the definition of a derivative, right? If we take the limit as delta t becomes very small, then that's just the derivative of the extensive property in system 2. So what we're going to do, we're going to do that. We're going to take the limit as delta t approaches 0. And this is the definition of a derivative, right? We're taking the infinitesimal change with a very small delta t of this property. So that allows us to write the derivative of system 2 with respect to time. And we can plug these terms in. So basically we have, our extensive property times rho a v, where v is our velocity. It's not to be confused with volume. And we have our delta t. So this is, I'm going to call this the influx term. And this is going to be b rho a v. Again, this is velocity. This is going to be the outflux term. I forgot my delta t in there. And this is all divided by delta t. So these guys cancel, or I canceled out a bit too much there. So the delta t cancels. And what we're left with is, we find that the derivative of the control volume with respect to time is equal to the derivative of the system properties with respect to time plus b rho a v in minus b rho a v out. Okay? And there's one thing we want to do here. Since we wanted to apply the conservation laws of solid mechanics, which work with a system, we want to isolate this guy here, right? So that's the last thing we're really going to do. So what we can do is we can basically take all these terms on the left side, so take these guys, move them over here, isolate that guy, and that will give us an expression that we can apply our conservation laws that we're used to and translate that over to a control volume basis. So what we will find is that basically we have the extensive property B over system 2 is equal to the derivative of the control volume with extensive property B plus the flux term V rho A V, which is flowing out, and then you subtract the flux term which is coming in. So you end up with the following. And one other thing you can do is we can rewrite basically this term here. So the amount of the extensive property B over the control volume. Because initially, we found out what the extensive property is equal to in terms of an integral, right? That's what we went over when we were talking about intensive and extensive properties. So let's actually fill that in, okay? So what we can do is we can plug in that nice integral, which is over the volume. We can take our intensive property, take our rho, integrate over the entire volume. This gives us basically our CV term. So this gives us the extensive property BCB. That's a terrible B. Let me rewrite that. It's a little better. So we can integrate over this entire guy, and we had a derivative. All right. So that gives us a nice result, which is the Reynolds Transport Theorem in one dimension. And as I will show in subsequent videos, after I generalize this, we can take this form and we can apply conservation of mass, conservation of momentum, and conservation of energy, just as we would in solid mechanics, because we know how to relate the system properties to a control volume, and that will streamline the derivations of those conservation laws. But to wrap things up, let's take a look at this and see if it makes sense, okay? So I'm just going to check to see if I have enough room to write up. Yes, I do. So if we actually have, some kind of region we're analyzing, well, we're going to call our control volume. What we can say is, the entire amount of properties, like throughout this region, can change, right? So B, CV, or the extensive property B, it can change from changes inside that region, or it can change from properties flowing out or flowing in of that region. So this result makes sense, right? Because this represents, this term is, as I talked about previously, the total amount of an extensive property B over a given region. Or in our case, it's going to be this entire control volume. So it's all B within this region. So that's going to tell us how that changes with time, okay? So that's going to tell us the interior change of this extensive property B. And these terms are our flux terms. They tell us how the property is being carried out of or into the control volume. So as an example, maybe the density in here changes if we don't have a steady problem. And if the density changes, you're going to have more mass in a given region, and that's going to change your extensive property, right? So that's the interior change, right? But you can also have some fluid flowing out, and when fluid flows out, it pulls that out of that region, and that's where the flux terms come from. So this result, by applying some simple balances and mathematics, we get a result that makes sense. And, it jives well with our intuition. So that's a good thing. But this is the one-dimensional Reynolds Transport Theorem. We're going to use it and apply it to conservation laws in the future. And in my next video, I am going to generalize this result for any kind of region, not just a one-dimensional duct flow.